I want to talk about Involute Spur gears. I want to make a short series on this, and I've been wanting to do it for a little while. These are easier to design than they look. I have some equations that might help us out. These will probably mean nothing to you, but if you are someone who just tuned in the video to look for equations, here they are, right? This is a good starting point to design a gear from. So let's talk about some of the lingo that we see on these equations, and that will help us to calculate the values. And then we'll go in and design an Involute Spur gear in SolidWorks. It has been a while since I've used SolidWorks, so it'll be pretty fun. Let's go with pitch circle to begin with. This is a theoretical circle that represents the diameter of the gear if it were just modeled as a circle, right? You may think that you would model a gear as its outer diameter, like from the ends of the teeth, but as you can tell, since the teeth mesh together, you can't really simulate gears as their outer diameter because of the meshing. So the pitch circle is the diameter of the circle if the gear were just a circle, right? You can see that when the pitch circles are modeled, they are tangent at one point, and that's the proper diameter, or the pitch circle. So let's go to the addendum and dedendum, right? The addendum is the radial distance from the pitch circle to the top of the tooth. So that's pretty simple. Our green pitch circle to the blue top of the tooth, and then our radial distance from the pitch circle to the bottom or root of the tooth. The addendum circle then is the, you could probably think of it as the outer diameter. It's simply the pitch circle made by the addendum circle. The addendum circle is made, of course, by the pitch circle and the addendum added together. And you want to, of course, add two addendums to the pitch circle because we are dealing with a diameter, not a radius. And the same thing with the root circle, also known as the dedendum circle. You have the pitch circle minus two dedendums to get the root circle in navy here. Circular pitch. This is the distance from the surface of one tooth to the same surface on the subsequent tooth. So we're taking an arc length, and this always falls on the pitch circle, right? So we take our pitch circle, we go to the distance of one tooth, follow our pitch circle to the surface of the next tooth, and that is known as our circular pitch. The diametral pitch is a ratio of the number of teeth to the pitch circle. This is measured in pitch per distance. So in other words, I have 15 teeth. I have a pitch circle of 1.5 inches. So I say the number of teeth divided by the pitch diameter is 15 teeth per 1.5 inches, or 10 teeth per inch. The module is simply the inverse of that. So instead of number of teeth divided by pitch circle diameter, it's pitch circle diameter divided by the number of teeth. So if I take the same gear, it's 1.5 inches divided by 15 teeth, or 0.1 inches per tooth. The involute profile is probably the most important profile on the gear. The involute curve itself is part of a family of roulette curves. In this case, I would be wrapping a hypothetical string around something round and tracing the curve as I unfold the string around the circular object, and that makes an involute profile, right? Roulette curves are made in this way by unwrapping things around different shapes. So we want our teeth to have this involute curve, and that is what profile makes the teeth mesh correctly. The base circle, a diameter of circle that marks the start of the involute profile, right? So we don't start the involute profile at the base circle, or at the root circle. We start the involute profile at the base circle. So we'll have some calculations on how to calculate this base circle diameter. So given all that, here are the equations that we're going to make. And of course, we've just been talking about a bunch of vocabulary and lingo. It'll be a lot more helpful to just jump in and design a gear so we can see some of these principles and concepts that we've talked about in action. Here we are in SolidWorks, and let's go through actually making a gear. First thing, we'll go Tools and Equations, and that will allow us to create some global variables that allow us to update gears on the fly. It sure makes modeling a lot easier. So for global variables, let's start with the things that we are given. Given diametral pitch, which is P. I am typing these out so it's easier for newer people to follow along, so you don't have to look up the variables all the time. You can make the variables, of course, whatever shortened thing that you want. Let's say that this will have a value of 2. And then we'll add a variable. How about number of teeth? And let's say 35 arbitrarily. Let's add in a pressure angle. And we're going to call that 20 because 20 is a very common pressure angle. I did not talk about pressure angle very much, so let me just grab this real quick so I can draw this out. Right, you have two curved surfaces on this gear pushing on each other, and so the force is not going to go this way, right? It will not. No good. How the force actually goes from tooth to tooth is at an angle, right? It will head about this way. And if we draw that angle off of horizontal, right, that's usually about 20 degrees. So the two common pressure angles are 20 degrees and I believe 14.5. I'd have to double check, but it's 14 point something. And it's very rare you'd ever get any pressure angle that's not one of those. And if in doubt, go with 20. So that's what pressure angle is talking about. Next, let's go with, how about a pitch diameter? And pitch diameter ought to be number of teeth divided by the diametral pitch. So say global variables, number of teeth divided by, and then diametral pitch. Next, we'll probably want to add in a base diameter. That's, of course, the diameter of our base circle. That is the diameter of our pitch, or pitch diameter, and the cosine of the pressure angle. So we're going to say pitch diameter times the cosine of the pressure angle. Now it's very important. SolidWorks seems to default to radians, and so I'm going to come in here and say 20 units, and we're going to go to degrees to make sure that we're taking the cosine of the degrees. Next, I'm going to want to add in my addendum. That's going to be 1 over our diametral pitch. So we're going to say addendum and 1 divided by and with that diametral pitch, I can also say dedendum, and that will be 1.25 divided by our diametral pitch. So with our addendum and dedendum, let's start with our addendum diameter, and that will be addendum diameter. It's going to be our diametral pitch plus 2 addendums. So we're going to say equals diametral pitch plus addendum plus addendum. Next, we'll say dedendum diameter. And yes, diametral pitch plus, and I made a mistake there. We want pitch diameter, right? So pitch diameter plus dedendum, and it should be minus. So minus dedendum and minus another dedendum. Same thing here. I said diametral pitch when I should have said pitch diameter. So equals pitch diameter. And that is much more correct. Finally, for tooth spacing, of course, we can get the degree angle between teeth as 360 divided by the number of teeth. We, of course, want to modify this a little bit to suit our modeling needs. And so we're going to say tooth spacing equals 360 divided by 4 times open quote number teeth. And I put a minus sign there. I really need to have a multiplication sign. There you go. So 360 divided by 4 times the number of the teeth. And we'll say OK. So let's get modeling. The first thing I want to do is create a sketch on the front plane. We'll draw a bunch of circles. And these are just going to be references to make sure that everything visually looks all right. We're going to make sure that these are all for construction. You know what? Let's actually make this one not for construction. And let's assign some diameters. We're going to say equals global variables. We want this to be the addendum diameter. I'll make this one. We use the base diameter. This one equals the dedendum diameter, that would be the base circle. And this one will equal the pitch diameter. And everything seems to have snapped into the correct place. So we're doing quite well. Now we want to add an equation-driven curve, and this is going to be our involute profile. So as of right now, of course, I did not make our addendum diameter, or the outer diameter of the gear, a construction line, and that way we can extrude this, right? So next, let's go with, in fact, I could probably extrude this right now. And that would make it a little more simple going forward. Let's make this something like an inch thick. Doesn't really matter, you know, what dimension we give this, because this is an arbitrary example. But let's sketch here on this face. And I want to make sure that I take my sketch here and I show it so I can see all my little diameters here. So now we want to make our involute curve, and to do that we want to have an equation-driven line. We can find that on our sketch menu here, equation-driven curve, or tools, sketch entities, equation-driven curve. We wanted to use parametric instead of explicit, and we want to enter the following equation. We'll have pitch, nope, I actually want base diameter, and we'll multiply that by 0.5, and let's put that in parentheses. I believe British people call parentheses brackets, which is pretty cool. So if you're British, you can confirm that. Let's go with times cosine of t, and let's add another bracket or parenthesis, whatever you want to call it, times cosine of t plus t times the sine of t and 2 close parentheses. For the next equation, it's going to be just a tad different. We're going to say base diameter in quotes times 0.5. And we'll put that in parentheses just to make sure that the order of operations is clear, times, open parentheses, sine of t minus t times cosine of t, and we'll run that from 0 to 1. And that is an involute curve. So we have our involute profile right here, and it is the way that we mathematically entered it. So the first thing I want to do is make sure that it is fixed before I mess with anything. Then let's go to our center line. And I'm drawing a horizontal line as a reference. And then I also care about where our involute profile intersects with our pitch circle. So we're going to make sure that that's coincident. And then let's do something that's more concerned with tooth spacing, right? We're going to come over here. I can draw the same center line if I wish. We're going to add an angle from our line that intersects between these 2 points and here. And we're going to say equals global variables, and that's our tooth spacing variable down here. So that should work pretty well. Right, so this gives me the right kind of spacing because I'm going to make a cut to cut out this tooth profile. I'm going to draw an arc from my origin to here. We can just make this straight vertical. And we're fully defined, right? So there we have the beginnings of a tooth. Since I'm referencing this circle, right, this is the where we want the very, very base of our teeth to be. I think I'm going to correct myself, and I want to cut out down here. Make sure that our points are coincident right there. And there we have it. That's better. So we should have an enclosed entity, and SolidWorks should shade enclosed entities. So it looks like I just had to wiggle that point around because I was just about to bring up how that's not shaded. So we've got an enclosed sketch. Let's features, cut. We're going to say through all. And there's the beginning of one tooth. We'll select this as a plane since we used a mirror to cut with. That's a planar surface. And we're going to mirror our feature. And there you can see the other tooth. And then we can do a circular pattern. We can choose our center as the circular face. We're going to say equal spacing. We're going to say equals global variables, the number of our teeth. And we don't just want the mirror, we also want the initial cut. So we make sure that this says mirror and cut extrude. Could not find face or plane. So why don't we go back to our mirror, we'll edit the feature, and let's check geometry pattern here. And we'll do the same geometry pattern for our circular pattern. So we're going to say circular pattern. We can choose this faces our direction, equal spacing. We're going to say equals the number of our teeth. Make sure that we have geometry pattern. And that fixed it. So there we have an involute spur gear. Let's just put a hole in the middle. Now I don't expect anyone to follow along. Let's make an assembly and just put two of these together and see how they visually look to us. Alright, so I got this set up in an assembly, and I have a gear mate going. And if you don't know how to do a gear mate, it's mates, go to mechanical mates, and the 2021 interface is a little bit different than the previous ones, but you always have the option for mechanical. So go to mechanical, and you can choose gear down here after you select two round surfaces from the gear. And it looks like we are meshing very well. So this is how an involute gear works, because it meshes in a way that you don't get clunk, 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 clunk between the teeth, right? You just want it to be perfectly silky smooth. So you may invariably be asking, okay, but what if I'm on a CAD platform that I can't run an equation-driven curve? You're not out of luck. So in the next video, I want to talk about an alternative to running equation-driven curve gear teeth. We can run an approximated gear tooth. And then in a video after that, I want to examine whether or not the approximated method is valid for actually using gears, or if it's so approximated that you would never be able to use an approximated method to actually run gear teeth. Okay, I almost forgot to demonstrate the whole point behind using the equations here. So let's manage equations and just go through this real quick. I like to check the automatically rebuild box. And the beauty of this is we can change, say, our teeth to 10 teeth, and the gear updates. I can change my pressure angle to 14.5, the other common pressure angle in gears, though I tend to always recommend 20. We can make this have maybe 15 teeth, right? So we can alter the gear pretty much instantaneously, right? We can give this a higher diametral pitch if we wish, and you can see that the gear just updates exactly the way that we want to. So if you're going to model gears, I highly recommend using equations because it really is so much easier. So with that being said, you should have a fully customizable gear. You can download this from GrabCAD if you wish. Again, I hope this video was helpful. If it was, please subscribe. I'll see you in the next one.